So in the last class, we were seeing the Aloha concepts, right? The one of the uncoordinated access. In that we have seen the random access and the carrier sensing multiple access, right? Carrier sensing protocols. So yesterday I was just introduce what is the random access protocol, and in that the pure Aloha. So its basic principle and how it works with a clear diagram. Then how to choose the random number using the number of attempts by the sender or the source. Then how to calculate the backup time where the source has to freeze for some time, right? Then so the complete operations I have captured in an algorithm, and we have developed this algorithm, right? Then finally, we have introduced the efficiency of the pure Aloha, right? So I'll just write about that. So yesterday I gave little bit about the efficiency, right? So efficiency. So this is the today's complete, uh, you know, concepts which I want to introduce. Before this, the pure Aloha. So I'll be calling as the PA, right? And the efficiency for the pure Aloha, we have got it directly. We have taken, we have not derived. It's G into e raised to minus 2G, right? Where G is the number of users wants to transmit the frame in the time period that we call TT. So this is the time period within which the frame has to be transmitted from source to the destinations, right? And I have told that we in order to calculate the maximum efficiency and max, right? So in order to calculate, I need to differentiate the above equations, right, with respect to the G, and I need to equate to 0. Right. So if you differentiate this equation, so what I will get G into differentiation of e raised to minus 2, G is minus 2 into e raised to minus 2G, right? And the plus. So now I need to differentiate the first term. I need to keep the second term. So differentiation of G with respect to the G, it is a 1, right? And I need to keep the e raised to minus 2G as it is and equal to 0. Good, right? So in this, so we are having the common term e raised to minus 2G, right? E raised to minus 2G. So it's a minus 2G plus 1 equal to 0, right? So take this term in the right side. So 0 divided by anything, it will be the 0, correct? So what I will get minus 2G plus 1 equal to 0, right? So this is the equation number 1, right? So in order to satisfy this equation, so I want to do LHS equal to RHS here. LHS equal to RHS. So in order to make LHS equal to RHS, so what value I need to choose? G, it's a 1 by 2, isn't it? Should be the 1 by 2. Then only I can make this equal to 0. Correct. This 2 and this 2 will get cancelled. Minus 1 plus 1 equal to 0. That's the reason in the last class I gave G equal to 1 over 2. Okay, G equal to 1 over 2. So if you draw the graph of the efficiency, suppose here if I draw, so x-axis is the number of users wants to transmit the frame in TT amount of time versus the efficiency, right? So if I draw, so the curve will be something like this, right? And this is the maximum where I can get the efficiency, right? So this is the maximum efficiency. So where I say here the n max, right? So this one, what we call is the 1 over 2 into u, and that yesterday I wrote that is a 18%, right? And how I we got when we take g equal to 1 over 2, right? So whatever the value we are getting here, so this value, if I put it here, so that is the maximum efficiency I can get. So that is the 18%, 18% of the efficiency. So this was the uh, derivation of the maximum efficiency and deriving the g, that is the number of users wants to transmit data in tt amount of time, that is a g equal to 1 over 2. And yesterday I have told g equal to 1 over 2, right? 1 over 2 means g equal to 1, the one and a half users, correct? One and a half users will be sent in tt amount of times, correct? And for the one user, right? For the one user, so it will be 2 times tt. So this is the time I said yesterday, the vulnerable time. So vulnerable time means where the more than one stations or the devices will start sending the frames. As a result, they will get collided, right? So there will be loss of the frames, correct? Okay. Fine. So now today I will introduce about the slotted Aloha. So why we have to go, and the if time permits, I will talk about the CSMA, different carrier sensing multiple access protocols are there. Right? So the very first one, the slotted Aloha, I'll be calling as a SA, right? So the problem which was there in the earlier, right? Earlier means the pure Aloha, where we have considered the one, the link, right? The what we call the medium, correct? And there are various number of devices which are connected to this link and they are accessing this link. Suppose this is the A and this will be the B and this will be the C. Right? So everybody wants to access the only one link, right? And in the pure Aloha, we have got the vulnerable time as 2 times the time it requires to transmit a frame, right? And the efficiency we have got, that is the maximum efficiency, right? That was around 18.4 actually. So roughly we can say the 18%. Right? And this is the main issue. So vulnerable time, the 2 times the time required to transmit the particular frame, right? That is a vulnerable time, and the maximum efficiency is 18%, and that is not a good idea, right? So vulnerable time is also more. So what we can do, what is the solutions we can develop in order to reduce this vulnerable time? So I want to reduce this vulnerable time and I want to increase this efficiency, right? So for that reason, the slotted Aloha has been evolved. So the name itself, it says that the slotted, the pure Aloha, and this is the slotted Aloha. Slotted, right, means whatever the time period is there. So that time period, I'll be putting it as a slots. I'll be dividing into the number of slots, and each slot, right, the width of the slot should be the width of the frame, right? So with this brief introduction, I will give a pictorial view of slotted array. So these are the 4 stations wants to send the data, right? Yeah, this is the time period. So as I said, that time is divided into the number of slots like this: slot 1, slot 2, slot 3, slot 4, and so on, right? And for the station A, this is the time period, and for the B, and finally for the C, right? So as I said, this is the slot 1, this is the slot 2, and this is the slot 3, and this is the slot 4. Okay, and so as I said, the slot length, right? So this is the frame, correct? So whatever the frame length we are having, so the same length will be having the slots. Okay, so length of the slots are equal to the length of the frame. So suppose the station A wants to send, right? So it can send at the beginning of the slots. Okay, but in the pure hello, what is to do? So whenever the station A has the frame, just to send it. Whenever the B has the frame, just send it. And whenever the C has the frame, just send it. But here it is not like that. Only at the beginning of the slot, only the station, for example, station A wants to send a frame, only at the beginning of the slot it can send. Suppose B has the frame at this point, right? Maybe, for example, you can consider it at the time T1. It has the frame, but it won't send. It will wait for the next slot. So here it will be sending like this, right? And suppose the C has a frame, maybe, for example, at this point, right? T2, right? So it will send at this, right? For example, the station D, right? It has a frame at the point. For example, you can see that T1 dash, which is a less than T2, right? So as I said at the earlier, right? The slotted Aloha, okay, the each stations will send the frame at the beginning of the slot. So here, this is the beginning of the slot. So it will send the frame, right? So you can see here easily, the collision will be occurring at this point, correct? Right? So vulnerable time, how much here? The vulnerable time is the TT, correct? So TT is the time it requires to send a frame, right? So here the first objective, I wanted to reduce the vulnerable time. So I have reduced into TT. So earlier it was 2 times TT. Now it is the only 1 time TT, right? So the collision will occur only in this time period. Good. Now, uh, yeah. Now we'll calculate the efficiency, right? The efficiency we need to calculate it, right? In earlier case means in the pure Aloha, we have taken efficiency equal to G into e raised to minus 2G. So we need to derive that equations, right? But in this case, right, in the slotted Aloha, the efficiency eta equal to G into e raised to minus G. So I'm not, again, I'm saying I'm not deriving the equations. Okay. So G into e raised to minus G. So it's a very bad. I'm sorry. G into e raised to minus 2 times, sorry, minus 2G minus E G. Sorry, again it is coming. Oh, yeah, G into e raised to minus G, right? And in order to calculate the Nmax, right? So again, I need to differentiate the above equations with above equation with respect to G, and I need to equate it to 0, right? So whenever you differentiate, right? So I'll get the expression, final expression like minus G plus 1 equal to 0, right? So in order to satisfy LHS equal to RHS, I need to choose G equal to 1. right? Then only this equation will be valid. -1 + 1 equal to 0, right? So maximum efficiency will occur at G equal to 1, right? So if you put G equal to 1 in these equations, eta, right? So eta 1 e raised to -1. So this is the maximum efficiency we can get it from the slot. I mean slotted Aloha. So if you calculate e raised to -1 or 1 over e, right? It will be around 36.8, 36.8%, or roughly you can say it as the 37% efficiency, right? So in the earlier case, we got just the 18%, right? So it's almost the double, right? So you can draw the efficiency diagram. So it's a G and this is the efficiency, right? So earlier we got something like this, correct? So it's a G equal to 1 over T here, and we got the efficiency as 18% for the pure Aloha, right? Now for our case in the slotted Aloha, right, it will be more than that, correct? So it will be like this. So this is the G equal to 1, and here, right, it's a 36%, 37% efficiencies, right? So the both objective which we were having in the earlier, right? So I have to decrease the vulnerable time. So I have decreased into the T, and it was the 18 or the 18.4% efficiency was there in the pure Aloha. Now I have increased into the 37% of the efficiency, right? So now at least we can reduce the collision, and we can reduce the vulnerable time using the slotted Aloha, right? So this was the complete the random protocols, right? Now we will study the carrier sensing protocols, CSMA, carrier sensing multiple access protocol, CSMA. Right? So in the Aloha and in the slotted Aloha, actually two important things they won't do. The very first one, the very first one, they won't, they won't listen the link or the medium, right? So whatever the medium we are having, right? So like this was the arrangement, correct? So like this was the arrangement. And these stations A, B, and C, and so on, right? So in the pure Aloha, whenever they have the frames, they will send it. And in the slotted Aloha, at the beginning of every slot, they will transmit the frame. But in both the cases, we are having the collision. But main problem is, see, they are not listening to this medium, whether other people or other stations are sending the data or the frames or not, right? So that is the main drawback in the previous cases in the pure and the slotted LR. So they won't listen the medium or the link or the channel before transmitting the frame, right? And in the second one, they don't stop whenever the collision occurs, right? In the both the cases here, right? So here, whenever collision occurs, they won't stop transmitting the frame, right? So they will just transmit it, right? They won't bother about whether it is collided or not. Once if you receive the negative acknowledgement, or after timeout, if you are not before timeout, we have not received any acknowledgement, then we will say that so there is something problem with respect to the medium, right? Due to the more congestion, right, or due to some other uh, you know constraints, they are not able to transmit it. Right? So the second one, which I have mentioned, that they won't stop. They won't stop whenever they collided. Right? They won't do that. They won't stop. Right? So this is the basic problem in this random access protocols. In order to solve this, the people or the scientists have come up with the carrier sensing multiple access. This is carrier sensing multiple access, right? So here the CSMA requires that each station, the very first one, they will listen to the medium, right? So here, very first one, the station is there, right? Suppose the station S is there, right? S1. Very first one, they will listen. Is anyone transmitting the frames or not? They will listen using the different techniques. So we are usually we have to check the frequency or any signals are going from one place to the other place or not. Right. So they will check that one. Right. So in other words, what we can say is that CSMA, right? It's a based on the principle of sense before transmit. Or in our case, in our day-to-day life, listen before you talk. So the same concept, the CSMA is utilized, right? So here the CSMA reduces the possibility of collision. So in previous case, right, we are not reducing the possibility of collision, right? And in this CSMA, it can reduce the collision, but it cannot 100% eliminate it. Okay, so we'll see one example of the CSMA, how it will work, right? So consider the station A and it's a time period, right? So this is the time and station B. So this is time. And I'm having the third station C. Okay, and finally I have taken the fourth station as the D. Good. So these are the stations, right? So the first thing here, right? As I said in the earlier, the basic principle of CSMA is sense before transmit. Suppose station B, right, at the time T1 wants to transmit a frame. So what it does, it will sense, is anybody sending the frames or not, right? So has it sends, so at present nobody is sending, right? So what it does is it will start sending the frame, right? So this is how it will look, and this is the, suppose if you are taken this much of the propagation time, so it will look like this, right? So station B start sending the frame at time T1, right? Because none of the stations are sending the frames, right? Okay, good. No issue till now because none of the frames or none of the stations are sending the frames. But station C, right? At time T2, at time T2, it has a frame and it wants to send it, right? So what it does in the first first um, step is it has to sense it, right? So at this time, at the time T2, so none of the stations are sending it, right? Because see here the time T1, right? And this B's stations frame the first bit of frame will be reaching at this time, right? You can think of this is the T1 dash. No, not T1 dash. You can think of, okay, T1 dash, okay, T1 dash. The station C is receiving, right? But T2 is less than the T1 dash, right? C doesn't know whether the station B is sending or not because it has not received. First bit of the station B, it will be receiving at time T1 dash. But I'm saying before that, the station C wants to send it, right? So what it does, it will send the frame like this. So if you consider, so sorry, messed up. Okay, right? And it will be sending like this. Okay. Good. Can I change the colors? Okay. Yeah. Yeah, this is the station C's wants to send the frame. So it will be going like this way. Right. So, so here in these situations, right? So there will be collision will occur. When? So this is the point where the both signal will get intersect, right? So at this point, both will, start colliding, right? So at this point, it was complete the only the beige signal, right? Or beige signal, right? And here, correct? This. If you see this one, this is the collision, right? So both the signals have collided, correct? And again, this area, right? Only the siege signal is there, right? Even though the sensing method has been employed in this technique, right? But still we are, you know, getting, collided with the other station's frames, right? So C gets to know at this point there is a collision, right? And B will get to know the collision at this point, right? Then they will differ with each other. So this is the basic principle behind the CSMA, right? But here you might have observed in the earlier case, I have mentioned that the vulnerable time in the pure Aloha, it is a 2 times T, and in the slotted Aloha, it's a only, where is that? In the slotted Aloha, it is a only the TT, right? But in this case, right? In this case, it's a propagation time, right? So this is the propagation time. Whatever the frame it is going from here to here, right? So it's the propagation time. So vulnerable time here is equal to T times TP. So vulnerable time in the CSMA, it's a TP. So the amount of time the frame will take to transmit from one station to the other station. That's all. So that is the propagation time, right? So here actually, in order to avoid, right, in order to avoid this kind of a collision, right? Where the shaded area I have shown, this is the collision area. So I want to avoid this one. So maybe the station might have, waited for some more time, right? Then it could have taken the, very good method for scheduling the frames, right? But unfortunately, it has started at a T2 and end up with the collision, and it has to again retransmit the same frame, right? So what should a station do if the channel is busy, and what should a station do if the channel is idle? So these two things we need to understand, right? So one is the station. If it is busy, what has to do, right? And when in the station it's idle, what it has to do, right? So here, right, the station C at time T2, it was like feeling like nobody is sending the data, right? And it has sent it, but then also we have collided, right? So different scenarios we need to consider. So in order to sense the carrier, we have the three methods, right? To sense the carrier or the medium, right? We have three methods. Three methods we are having. So the very first one is the one persistent. PERSISTENT. One persistent. Okay. I'm very bad in rating using the mouse. Okay. So in the one persistent, so I have considered two cases, BG and the idle, right? So suppose the channel is BG. Okay, this is so double it indicates BG and single it indicates the idle. So here it is idle, right? And here it indicates the BG. Okay, BG. So the stations will sense, and here it will sense, and it feels that it's a BG. So continuously the stations will be sensing it. So at this point, right, whenever it senses, right, it's a idle, right? At this point, it's a idle. So here, whenever the station senses it, so it says that it's a idle, right? So here in this method, one persistent, whenever it senses it is idle, so it has to send it the frame. Just transmit. Just transmit the frame, right? So in the algorithm part, we can write it like this. So channel, right? So it's a channel, and we are having the two conditions here, right? One is idle, and another one is busy. If it is busy, then sends it. If it is busy, then it sends it. So continuously it will send it. And if it is idle, then transmit the frame, right? So in this method, after the station finds the channel or the link idle, it sends its frame immediately with the probability of 1. With a probability of 1, it will 100% it will send. If it, channel is free or idle, 100% it will send. That's the reason here 1 has written with a probability of 1, right? But this method has the highest chance of collision, right? Because in the earlier case, right? In the slotted Aloha, it looks like a slotted Aloha, right? Suppose that everybody is sending the frame at the starting of the slot, all the stations has to send, right? Suppose I'm presuming that the channel is idle at the beginning of the slot, right? So all the stations will start sending the frames. So as a result, there will be highest chances of collision, right? So this is the very first method they have developed it. Now, second method is a non-persistence. Non-persistent. STNT. Non-persistent. So here what happens? The same method, right? So this box indicates the BG. I'll write a B, and if it is a single line, it's a idle, right? And continuously the stations will be sensing the channel, and whenever it busy, so it will continuously senses it, and at one point of time, right? At one point of time, it is idle here at this point. It's a idle, right? Whenever it senses it idle, right? Then it has to wait for some random amount of time. So this is the random amount of time, and again it has to sense it. Again it has to sense it. And if it is idle, then only it has to transmit. I'll write TR. Okay, so I'll put it in the algorithm or in the flowchart format. So this is our channel, right? This is our channel, and the station, suppose station one is sensing, right? And it has two possibilities. The one is idle, right? One is idle, and another one is a busy, right? So whenever it is busy, right, it has to sense it. Whenever it is busy, it has to sense it, correct? And whenever it is idle, then it has to, right? It has to wait for some random amount of time. Wait randomly. Wait randomly, right? And again, it has to sense it. Okay. So I'll put one more channel here. So I'll put the now C, so channel, right? And if it is busy, right? So it has to again sense it, right? And suppose it's not a busy, right? If it is a idle at this time, after waiting or amount of time, it has to transmit it. TX. Okay. So sense it, and if it's idle, wait for some time, and again sense the channel, and again if it is idle, then transmit, right? Suppose if it's a busy, then again you sense the channel, and again whether it is idle or the busy, right? So this mechanism you need to do it at each and every stations, right? So this method reduces the chances of collision at a time, right? Because it is unlikely that two or more stations, right, to send the simultaneously. For example, the random number, I have said that it has to choose between 0, 0 and 1, right? So we'll get so many numbers, right? Maybe 0 or 100 you can say. Again we will get the different number of or different numbers. So with that number, we will be calculating the waiting time, correct? So very less chances of getting the collision, but never knows. Both can have the same some bad luck, right? So that is the again the collision can occur. Suppose two stations chooses the same random number, right? So that's the non-persistent. The third one is the p persistent. P persistent. Okay. So I'll complete with this. So in the P persistent, what happens? Same thing, whatever we were discussing earlier. So busy and the idle, right? So the channel is busy. So whenever the channel is busy, the stations will continuously census the channel, right? So after busy, right? If the channel is idle at this time, right? So what it does is it will wait for a slot. It will wait for some random amount of a slot, right? So it's like a probability outcome doesn't allow the transmission in this time period, right? Again, we will be calculating the some probability. So for example, p equal to 1 over 2 is there. So at that time, it may or may not send the packet, right? So these are the slots. It has to wait after certain, and after waiting this slot also, I will again calculate the p value, right? So the probability of outcome, whether we can transmit it or not, right? So once it's within that, then we can send the or we can transmit the frame, right? So here we use the back of process, right? In this method, if the channel has the time slots, which we have done it in the slotted Aloha with a slot duration which is equal to or greater than the maximum propagation time, right? So the p persistent approach, it will combine the both the previous approaches, advantages of the previous approaches, right? And it reduces the chances of a collision and improves the efficiency, right? So in this method, after the station finds the line idle, which I have shown here, right? It follows the main two steps, right? So with probability of P, the station sends the frame after waiting this slot 1, slot 2 or slot 3. So how many number of slots are there, right? Depending upon the P value, right? Which we will be calculating using some parameters, right? And with the second point, with a probability of 1 minus P, right? The station waits for the beginning of the next slot, next time slot. And again, the stations again it is senses the channel, and if the if the link is idle, it goes to the again the first step, that is the again it will calculate the probability P, and this and if it is within the range, it will send it. Otherwise, again it has to wait. So this is the process the P persistent will be having, right? So with this, I'll stop the class. And if you are having any queries, please ask.